Hi guys, so in this lecture we'll be continuing on our case 4, which was double bond conjugation with double bond. So let us look into some more examples. So we have something like this. A benzaldehyde CHO here. So what would happen is, if you actually draw the structure with all the bonds here, you can clearly see that this is the structure. Now what will happen is, the O will withdraw its electron from the bond, making a carbocation and a negative charge on itself. H and O minus. So now what will happen is, this pi bond will jump over to, because of the conjugation of pi bond and a positive charge, to form a positive charge carbocation on this carbon and CHO negative here. What next would happen? Again this one. So we would have something like this, positive charge here and a double bond here. Now again this will happen, resulting into double bond here, here, and a positive charge here. Again what will happen is, this double bond will come here, and the negative charge on oxygen atom will again come here, forming the compound, forming the original compound. Okay, so this is how the resonance happens in this case. And what would be the resonance hybrid? Hybrid would be something like this, wherein all the carbon atoms in the benzene ring are involved here, with this carbon atom as well, double bond here as well, and double bond here as well, with a partial negative charge on oxygen, and on rest of the carbon atoms it will have partial positive charge. So it was having here, here, this side and this side. Okay, so let us look into another example where we have again what will happen is, the breaking of bond will happen, this bond will happen, and this will result in formation of carbocation here and a carbanion here. Now pi bond conjugation with positive charge will result into positive bond, positive charge on this carbon, and a double bond here. Okay, now again what will happen is, so with this we have positive charge, we have a positive charge on this carbon atom, so in the hybrid. So after this what can happen is, actually again the negative charge can come here, and again the pi bond can shift to this vacant p orbital, resulting into the previous compound, the original compound. Okay, so what would be the resonance hybrid here? I think you can draw, with the double bond conjugation between all the three carbons, and partial negative charge here and positive charge on this carbon and this carbon. Okay, let us take third example, where we have something like this. So I am directly drawing the resonance hybrid. I hope you can draw the resonating structures in between. So this would how it would look like. Oxygen would have a partial negative charge and a partial positive charge on this carbon atom and this carbon atom. Okay, so now we'll look at case 5, in which we have d orbital resonance. Okay, so if you look at the example of it, let's suppose I have CH2 and a negative charge on a carbon atom and single bond chlorine atom. So if you look at the hybridization of chlorine, it is Ne 3s2 3p5, and 3d is a vacant orbital. Okay, so what will happen is this negative charge will form a bond with chlorine atom by, as the chlorine can accept its electron in its vacant d orbital. Okay, so hence this is the d orbital condition, and if you look at the resonance hybrid, it would be something like this: partial negative charge here and partial negative charge here. Okay, and again if you look into examples like something CH2 minus SH, again d orbital resonance can take place here because S has vacant d orbital. Third example can be, we have something like CH2 minus here and PME3 here. So what can happen in this case is, again P has a vacant d orbital, again this will take place. Now let's discuss the case 6, where we have one positive charge and lone pair on adjacent atoms. Okay, so case 6 is when positive charge and lone pair on adjacent atoms. Okay, so what does this mean? Suppose we have something like this. So here we have two lone pairs on oxygen atom and a positive charge on the adjacent carbon atom. So what will happen is oxygen will take the positive charge on itself, and resultant would be a double bond with the neighboring carbon atom. Similarly, if we have something like this, again we have one lone pair on the nitrogen atom and a positive charge on a adjacent carbon atom. So what will happen is the lone pair will come in conjugation, the lone pair will come in to form bond between nitrogen atom and the carbon atom, thereby incurring a positive charge on nitrogen atom. Again we have something like this. What will again have to happen is, again positive charge and lone pair are in conjugation or in addition to each other. So sulfur will donate its lone pair to form a double bond between itself and the carbon atom. Okay, now we will be studying about the relative stability of resonating structures. Relative stability of resonating structures. Okay, so in this, suppose we have a compound like this, and we have its resonating structure. So which of the two compounds is more stable? Suppose this compound has X bonds, then this compound is having X plus 1 bonds. Hence this compound would be more stable, high stable, or rather highly stable. Okay, why? Because in this compound, this carbon atom is having incomplete octet, whereas in this compound even there is one more number of covalent bond, and all the atoms in this compound are having complete octet, hence this is more stable. Okay, if we look at second example, where we have to compare the stability of this and its resonating structure. So in this compound, if you can see that this compound would be highly unstable. Why? Because we have a positive charge on a more electronegative element or atom, which is O, and in this case the positive charge was on less electronegative element, but in this case positive charge is on oxygen atom, which is more electronegative than C. Hence this would be stable, relatively stable than this compound. Okay, let's look at this example where we have this, and this gets converted into something like this. This lone pair actually, Cl donates its lone pair to form something like this compound. Okay, so which of the two will be more stable? This would be highly stable. Why? Again, we have positive charge on chlorine atom, and here it was neutral, hence positive charge on electronegative element in a compound is more unstable than a neutral charged electronegative element, or no charge on electronegative element. Let's look at the fourth example. Here we have this compound and its resonating structure something like this. So which of the two is more stable? Obviously this is more stable. Why? Because negative charge on more electronegative element, which is O, is more stable than negative charge on less electronegative element. In this case it was carbon atom. Let's look at the last example of this lecture. We have something like this, a positive charge here, and it converts into double bond here and a positive charge on this carbon atom. Okay, so which of the two is more stable? If you can see that for this carbocation, the inductive effect of this and 3 carbon atoms are involved into the picture. But if you see this carbon atom, so only this carbon atom has a inductive effect of only this carbon atom, which is also sp2 hybridized. Hence in this case inductive effect of the ring is less than in this case where the whole ring was involved in the inductive effect. In this case what will happen is these carbon atoms are involved in inductive effect for the sp2 hybridized carbon atoms which are available here because of the double bond. Hence inductive effect in this case is more than this case, hence this would be more stable. Okay, here also inductive effect is there, but its inductive effect is shielded by the sp2 hybridized or double bonded carbon atoms, so that the net inductive effect of these carbon atoms on this positively charged carbon atom is reduced, hence this is more stable. So with this we come to an end of this lecture. So we'll meet in the next lecture. Till then, good luck and goodbye.